Hello and welcome. We were studying instrument transformers, that is CT and PT, but they are basically transformers, and to know them in more detail it would be better if we just review some concepts, some basic concepts of transformer magnetic circuits, which you might have already studied in an electrical machines course or maybe circuit theory course, etc. So this is an additional video. We will review some concepts. We cannot prove everything in one class. That's not possible. But we will review some important concepts which will help us in a better understanding. Okay. So let us start with the simplest concept of inductance. Okay. Now inductance can be either self-inductance or mutual inductance. Okay. So let's first talk about self-inductance. What do we understand by this word self-inductance? If we have a coil which is carrying some current, say I, okay, let me use lowercase letter in this class to denote time varying quantity. IT is a time varying current. Now when this current I flows, it will create definitely some magnetic flux like this, so on. And if IT is changing, then this flux, if I call it phi, this will also be changing with time. Okay, if current is changing, flux phi t will also be a function of time. And then we define the quantity called psi, which is phi multiplied by the number of turns. This is the number of turns of the coil. Okay. So phi is time varying, therefore psi will also be time varying, and this is called flux linkage. Now psi is time varying, and therefore we can find or estimate this quantity ddt, that is the derivative or rate of change of psi with respect to time. So this will be a non-zero quantity because psi is changing with time. And then Michael Faraday said that if psi is changing, it will cause a EMF to be induced across the two terminals of this coil. So between these two terminals, some EMF will be generated, called that E, that is given by d dt of psi t. This is Faraday's law. Okay, according to Michael Faraday. Now this can also be time varying, so it's a function of t as well. And now we know that psi is proportional to phi because psi is phi times n, and phi is actually again proportional to the current IT. More the current is, more will be the flux. Therefore we can write from this that Et, which is equal to ddt of psi t, will be proportional to ddt of IT, because psi is proportional to I. Okay, so therefore we can write this as some constant, proportionality constant, multiplied by ddt of IT. These two quantities are proportional to each other, so we bring a constant of proportionality and replace this proportional symbol with an equality symbol, and this constant of proportionality is called the inductance or the self-inductance of the coil. Okay, so this you all know, I hope. Now, next important concept is the scenario when, say, IT is pure sinusoidal, pure AC. Okay, so then we can often express IT as an exponential e to the power j omega t, omega being the angular frequency. And then we know, then if this is sinusoidal, of course, this is sinusoidal, then this will also be sinusoidal with a phase lag of 90 degree. Okay, so just recall this: if this is sinusoidal, this is also sinusoidal with a 90 degree phase lag. Okay, then ET is also pure AC with same frequency, omega, but lagging or leading, or that will actually depend on. Okay, so so let me just write, but out of phase from IT by 90 degree. Okay, this much I can write. Now, this is another important concept which you know. Now, let me ask the question that if this is the coil, if and it has a current IT which is AC. Okay, let me ask a basic question. What does this symbol, what does this arrow mean? What is the meaning of this arrow? Because you may say IT is AC, so it is changing its direction every cycle, I mean every half cycle. So why do we put an arrow? Because we know the current is sometimes flowing in this direction and rest of the time in the opposite direction. What does it mean when we put this arrow? This arrow is it is not the direction of current at all time. It is the chosen positive direction or chosen reference direction of this current. Okay, so this arrow, this is the reference direction. What do we mean by this? We mean if we write IT is equal to, say, some I cos omega t, and if we draw this circuit with this arrow and IT here, okay, so then it means that, say, at t equal to 0, then from this equation we know IT is equal to how much? It's I. Okay, say this I is a positive number, then at t equal to 0, the current that flows is I, but in which direction? That is in this direction. Okay, IT is this much. Okay, or let me write it this way instead of using the mod sign, it may be confusing. So let me write here that I is positive. I is a positive number. Okay, so at t equal to 0, the current that will flow, its magnitude will be I and its direction will be along the arrow. So along the arrow. Okay, but say at t equal to or say at omega t equal to 180 degree. Okay, 180 degree means pi, then that means when t is equal to pi by omega, okay, so at this moment it will be equal to minus I, which means at t equal to pi by omega, current flows in the direction opposite to the arrow. So this is the meaning of this symbol, this arrow in case of an AC. This is also maybe very obvious to you. Okay, so now let us ask the question that, okay, so Michael Faraday said the value of the induced EMF at any moment is given by this or by this. Okay, so this is the expression of the EMF, the value of the EMF. Now say if I connect an oscilloscope, okay, suppose if I connect an oscilloscope, then we will see that this voltage is varying sinusoidally when this current is also sinusoidal. Okay. Now I can ask that at t equal to 0, which terminal among these two, call them A and B, which among A and B will be positive at t equal to 0 or at any other time? Okay, which terminal will be positive? We know the magnitude is given by this, but what will be the polarity? Okay, now the polarity can be found using Lenge's law. Okay, so next important concept, this also you probably know, the polarity of the self-induced EMF, which is Et is equal to ddt of It multiplied by this constant L. The polarity of this can be found using Lenge's law. How? Okay, let's see that. So if this is the coil and these are the two terminals, the current I is like this. This is the chosen direction. Okay, now say at any instant, say at any moment, It is, or say this current this derivative of this current is greater than 0, which means what? This current which is entering the coil through terminal A, this current is increasing. So this means the current that is entering the coil is increasing. It may also mean actually that the current that is leaving through A is decreasing. Same, equivalent. Okay, but we say this current which is entering is increasing. Now, so it will generate an EMF whose polarity, I am telling you the answer, whose polarity will be such that this side is positive and this side is negative at this moment when the current is increasing. The entering current is increasing. Okay, then so say at any moment this is greater than 0, then side A or terminal A will be positive. Let me quickly justify this, very quickly. So when I'm saying this is positive, this is negative, you think of this inductor, this coil, as a battery, as a source of EMF. So this source of EMF, this source of EMF, which has, or the battery, which has plus side here and minus side here, can try to drive a current if we provide a closed circuit here. So if we close this circuit, then this battery, you know, a battery, any battery will try to drive a current from plus to minus outside the battery, but inside the battery, of course, minus to plus. This is how a battery behaves. Okay, so this battery, this source of EMF, will try to drive a current in this direction. Okay, so induced EMF tries to drive the current in this direction, in this anti-clockwise direction, current anti-clockwise in this diagram. Okay, now so what happens, now you see that this current, this induced current, is actually opposing the cause of the induced EMF. What was the cause of the induced EMF? It is this IT which was increasing. IT is flowing clockwise and that was increasing, and this induced current is therefore flowing in the opposite direction. It is opposing its cause, it is opposing its own very cause. Okay, so IT was increasing, which was clockwise, therefore induced current, or the current driven by the induced EMF, is in the opposite direction. So that is in consistency with Lenz's law. It can never be in other way. This side positive, this side negative is not possible. This is not possible. This is plus, this is minus. Okay, so this is how we can find the polarity of the self-induced EMF using Lenz's law. Okay, just to remember it quickly, I use a thumb rule which I can share with you. For self-inductor, self-inductance, if the current self-inductance, say with two terminals, with terminals A and B, if current entering A, current entering through A is increasing, then A will be positive. So now you can extend this idea that if current entering through B is increasing, then B will be positive. Similarly, if current entering through A is decreasing, then A will be negative. Okay, like this. If this is the situation, this is say this is IT in this direction, but say di dt is negative, then this side will be minus, this side will be plus. Similarly, if we have, say, this is the reference direction of IT and di dt is greater than 0, okay, so that means current leaving through this terminal is increasing. So therefore this will be minus, because this is leaving current, this is not entering current. Okay, similarly, if we have current say entering through this, if this is the direction of it, and again say di dt is positive, then this side will be positive, this will be negative, okay, so on. So you can extend this rule. So this is the rule. If current is increasing and if entering current is increasing through a terminal, then that terminal will be positive. That's the rule for self-inductance. Okay. Now let's talk about another concept, which is mutual inductance. What is mutual inductance? If we have two coils, placed side by side close to each other in close proximity, and then if we pass some current it which is varying with time, then of course the flux created in this coil, which will be like this, okay, that call it phi. So phi will also be time varying, so phi t is a function of time, and this phi also goes through this second coil, not all the flux but part of it, okay. So the part of the flux goes through part of the second coil, maybe not through the entire coil but part of the second coil. So therefore we can estimate some quantity, call it psi 2, okay, psi 2, which is flux linkage of second coil due to current in first coil, okay. Let's call it this way, psi 1 2, okay. So current in first coil and flux is linked in this second coil, okay, which will be roughly, it will depend on proportional to phi, call it phi 1 because this is created by the current I1 in the first coil, okay. So it will be proportional to phi 1, it will also be proportional to N2. This is the number of turns of the second coil. Okay, so on this two thing, this psi 1 2 will depend. Now phi 1 is of course is again proportional to I1t. Now let's apply Faraday's law. Michael Faraday says any coil, if it experiences a change in flux linkage, will generate an EMF. So therefore, if this current is changing, this flux is changing, therefore the flux linkage in the second coil is changing, so an EMF will be created between the two terminals of the second coil, call it E2. This can be also a function of time, E2t. And Faraday's law says E2t, okay, so this is the EMF in second coil due to current in first coil, okay. So then we can write this is equal to ddt of psi 1 2 t. Psi 1 2 is the flux linkage of the second coil due to the current in the first coil. You can also call it E1 2, okay. So this is Faraday's law, and then this is proportional to ddt of I1t, and we replace the sign of proportionality by bringing a constant of proportionality, and let's call it M12. This is called the mutual inductance due to the current in first coil and due to the EMF induced in the second coil. Okay, call it M12. Now similarly, if we pass a current I2, if I2 in second coil is changing, then we will have an EMF in first coil given by, call it E21. If this is 1 2, then that should be 21 T is equal to M21 dit dt. Okay, di2t dt. This is I1. Okay, and this is also called the mutual inductance. We can prove that M12 is always equal to M21, and therefore instead of using the symbol 1 2 and 2 1 differently, we can just say it is M. We can prove it. It's provable, absolutely provable, but we are not doing it now. Okay, now okay, next thing is, suppose if I have, so next point, if I have two coils both carrying current IT, I1t and I2t, say both I1 and I2 are time varying, then what will happen? Then there will be some EMF induced E1 and E2. Then we will have two EMFs, E1t and E2t, E1 in across the first coil and E2 across the second coil. I'm not writing, I think it's obvious what I mean. E1 is the EMF across first coil, E2 is the EMF across second coil, and they both will depend on both I1 and I2. So E1 and E2 both will depend on both I1 and I2. So E1, this EMF E1 will depend on both I1 as well as I2, okay, because the flux linkage is created by both I1 and I2. Similarly, this EMF E2 here across the second coil will depend on both I2 and I1. Okay, so that's another important fact. Now the very important question is about the polarity of the mutually induced EMF. Okay, so let's go back a step. Let's come here. Okay, so here we know that this current I1 is changing, therefore we have this EMF E2 induced across the second coil, whose value magnitude is given by this term. But what will be the polarity at any instant, say at t equal to 0? Which side will be positive, this side or this side? So that's the question. Okay, so the polarity of mutually induced, so this is another point, EMF can be found using again Lenge's law. How? Let's take an example. So this time I will draw a transformer. So this is the core of a transformer. Okay, you can think this in 3D. And it has two coils. So let me draw it like this instead of drawing like this, because then the direction of the winding will be more clear. Okay, so this is one coil and we have another coil. Now say this is my chosen direction of I1t. Say at any instant I have this current increasing. Okay, then according to the rule of self-inductance, which we have seen just few minutes back, we can say that this side will be positive, this side will be negative. The self-induced EMF will have positive here because this current is entering and increasing. But what will be the polarity here? This side positive or this side positive? Okay, so to find that, let's first find the direction of the flux. Okay. So let's switch back to the overhead camera. Let's find the direction of the flux. So let's apply right hand rule. Okay, so this is the direction of the current. Here you can see this is the direction of the current. Okay, and therefore this is the direction of the flux. And this flux is increasing. Okay, call it phi. So since I1 is increasing, d phi 1, you can call it phi 1 because this is due to current 1. This is also increasing. Okay, so we have assumed this to be greater than 0, therefore this is also greater than 0. Now I'm telling you that at this instant, I'm telling you directly the answer. I'm telling you the answer first, that this side will be positive and this side will be negative. Why or how to verify this? So to verify this, let's assume if we had a closed path, then this EMF or this coil will act like a battery. So this you think now like a battery. So this is the battery with plus here, minus here, and this will try to deliver a current in this direction. So this is the driven current, possible driven current, possible because if there is a closed path, I mean, if you think the EMF is trying to drive a current, okay, I don't know what's the good English. Okay, it's possible driven current. Okay, and so now in which direction the current flows? The current here will flow like this. So like this, this and this. Plus to minus outside, minus to plus inside the battery, inside the source. Now what will be the direction of this EMF? Okay, let's look at once again from the top. So this is the direction of the current. So this is the direction of flux. So flux is now in the opposite direction. So this flux is in opposition to the original flux, which was the cause of the induced EMF. So this is in accordance to Lenge's law. It is not violating Lenge's law. Okay, so this side will be positive, this side will be negative. You can verify that the other possibility that this is plus, this is minus, will violate Lenge's law. Okay, so this is how you can do it. Now let me show you another example quickly. I will copy this diagram. I'll copy and paste it. Okay, so now what I will do, I will change the direction of the winding here. Okay, so this time I will take the winding in the opposite direction. It will go from the back and then like this. Okay, so you see this winding is now in the direction opposite to this. Okay, now if you do the same analysis, assuming that this current I1 is like this and this is increasing, so this flux is also increasing, phi 1 is also increasing, then you can show that this side will be positive and this side will be negative. This is according to Lenz's law once again. And here also I have to change this direction. Okay, so the current here now will be in the direction like this. So it goes like this and then this. So the current now flows like this. Okay, plus to minus outside and minus to plus inside. Once again, you can see that the direction of this flux is in the opposition of the main flux. Okay, so this is in the direction opposite to the main flux. So this side will be plus. So in general, I can now write that it's important that which side will be plus or minus, that depends on the sense of the winding. That will also depend on the sense of this winding. If I change the direction of this winding, then also the plus minus sign will be affected. Okay, so now which side will be positive in this second coil, that depends on the sense of the winding. Now, okay, so now in general, for a pair of coil which the polarity of the mutual EMF depends on the sense or direction of winding, how the coils are made, in which direction the coils are owned. Okay, so what we do, we generally, okay, often sometimes, I mean, we draw the coils like this. You have seen it. So this is a pair of coils, and if we denote this current as IT, then we know that this EMF, call it I1, and say this is there is no current in second coil, so we have only the EMF induced due to the first current only, call it E2. This is definitely given by, according to Faraday's law, M di1t dt But which side will be positive? Because in this diagram we cannot see the internal sense of winding. So often we denote this hidden sense of winding with a symbol like this. So like this. So we put a dot here and here, indicating that this dot means if the current entering the dot is increasing, then the other dot will be positive. So what's the rule? Once again, I repeat the rule. If the current entering a dot is increasing, then the other dot will be positive. Okay. Similarly, if this current is entering this dot and this is increasing, so the other dot, this dot, I'll put a dot here. So I have to put a dot here to indicate that this side will be positive. So now I can hide all these internal things. I can just put these dots. So I just put, say, a dot here and maybe here. Now this means the rule. Let me write the rule. If current entering a dot is increasing, then the other dot will be positive. This is called dot convention. This drawing is called dot convention, will be positive. Okay. So now you see this is increasing. Sorry, this is from left to right, and say this is increasing. So that means this value is positive. Then the EMF will be such that this side is plus, this side is minus. So in general, I can write that the magnitude of the EMF is this m di1 dt, and its polarity is such that the plus side is towards the dot if the current is entering the dot. Okay, so this is a correct diagram. Similarly, if I have a situation, just for explanation, if I have two coils with dots like this, okay, so whenever I do not draw the internal diagram clearly, some information is hidden, that information is conveyed to you through the use of this dot. And now these dots are like this, which means if say I choose I1t in this direction, if this is the reference direction of I1t, then the EMF induced here E2t will be, of course, m multiplied by di1t dt, and the direction of this EMF will be this side positive, this side minus. Why? Because this is leaving the dot, entering through dot. Okay, so that's the convention, that's the dot convention. If current, so for self-inductance, if current entering is increasing for self-inductance, then that terminal through which current is increasing is positive. And for a pair of coils, if current is entering through this dot, this terminal, the other dot is equivalent to this, so this side will be positive. Okay, that's the rule. Okay, then and of course one obvious thing, in this diagram, if I say di1 dt is negative, if this is negative, that means this current is negative. So then of course that means this side will be plus, this side will be minus. This, if so let me write it and then I'll erase. If di1 dt is negative, then of course this side will be plus, this side will be minus. but I do not have to put, sorry, this side plus, this side minus if this is negative, but I do not have to write it this way. I can still write it this way, plus and minus, because now this is negative. Okay, anyway this is negative, so the magnitude will automatically be negative. Okay, so I do not have to do it explicitly. So in general, I will always write the EMF as m di1 dt and put the plus sign towards the dot if the other current I1 is towards the dot. If I1 is towards the dot, then plus should be towards the dot. If I1 is away from dot, plus should be away from dot. That's the rule. And m in general is a positive number, for particularly for when we are considering only two coils. There are exceptions, forget that. Okay. So now next important thing is this. Okay, so let's go back. Okay, so let me just mention a point here which I forgot. Okay, so we know that ET will be 90 degree out of phase, and we also know that the current, so we say sometimes that, okay, so switch the context now. So now we have gone back to self-inductance, where we have a current through this coil, and so therefore some EMF will be induced. Small et is the time varying quantity. Okay, so this is the time varying quantity, and you know that we also have a concept of phasor. Say the corresponding phasor, okay, phasor value is I. Okay, let me put a bar. So this is the phasor, and similarly here the phasor is this. These are the symbol for the phasors. You know what they mean. Okay, then we also know that I lags E by 90 degree, but this is not complete. If I just say this is not complete, because I haven't shown the reference direction of E. Okay, so I have to show a plus and minus, then only I can say that this current lags this voltage by 90 degree. If I put the reference direction like this, plus here and minus here, okay, in the opposite direction, then I have to say I leads E by 90 degree. So these are some crucial, small, sensitive concepts you should be very clear about. You know all this, but maybe you haven't thought in this way before, so I am reviewing this. Okay, so therefore this symbol is important. If I put the plus and minus in this way, then only I lags E by 90 degree, which means, so let me draw here and then I will erase. Okay, so okay. Now I can draw the timing diagram like this. So if this is E, then I, so this is ET, not capital E, small ET, this is IT, IT will be 90-degree lagging. Okay. E, provided the E is chosen to have the reference plus here and minus here. If I had chosen plus and minus here, then that E would have been actually this. This is nothing but minus of this E. And then you see that this current is actually leading this one, not lagging that one. So this you also think a bit. It's better if you think yourselves, then it will be more clear instead of listening to me, I believe. Okay. Yeah, so one more point which I wanted to mention. So now this fact that I lags E by 90-degree and the magnitude of I is such that, I mean, this relationship holds. Okay. So EMF, now you know that this EMF, the maximum value of this EMF can be written as I mean, it will be L omega, not J, L omega times the maximum value of I. And in phasor, okay, when we write phasor to denote both the magnitude relationship and this phase relationship, we write it this way. Let me do it once again. No problem in doing it many a times. It will be our practice. So this is ET, corresponding phasor is, sorry, IT, corresponding phasor is I, and here ET is the EMF, E or V for voltage, whatever you call. This is the phasor. Then we know that E is equal to J omega L times I. This represents both the facts that E max is equal to omega L I max. So this is equivalent to, and E leads I by 90-degree. So that's the phasor information. So therefore, for mutual inductance also, if we have two coils, call this current I1T, and if we have the EMF induced, call it E2T. If the corresponding phasor, I have made a mistake. What is that? In the previous diagram, what is that mistake? I have forgotten the plus minus sign. Without the sign, this is meaningless. Okay, that's important. So here also, I have put the symbol for the current. Similarly, I put this symbol here, and then I put some dots. I should actually put the dot first and then the symbol. Okay, so I put the dots, and then this current is entering through the dot, so I choose the reference direction in this way. Okay, so this is the EMF, and then the fact that E2T is equal to M di1 dt. Okay, and this is the mutual inductance. We can denote it like this. So which means E2 max. Okay, call it E2 max. The peak value of the induced EMF, this is a sinusoidal EMF, so the peak value will be it will be omega m I1 max and E2 lagging I1. So these two facts are equivalent to writing the phasor relationship that E2 is same as J omega m I1. Okay, that's it. I mean, now we will go to transformers. Okay, so we have reviewed self and mutual inductance. Now let's go back, not go back, or let's start the discussion on transformer and its equivalent circuit. An equivalent circuit. Okay. Okay, we will start this talk with ideal transformer. Okay, what is an ideal transformer? Let me give a definition. So it is an I can define it this way. It is an electrical equipment with two ports. So it is an two-port electrical equipment. Okay, like this. So we draw an equipment like a black box which has two ports, 1 and 2. Okay, it is a two-port electrical equipment. That means it has two sets of terminals. You can call them as primary and secondary side. So we can apply some voltage across this or this. We can pass some current through this. So call this current I1 and say this voltage. Let me draw it this way. I1, this V1. Here we can apply some we will get some voltage if we apply some voltage here, and if I have a closed path, then I can also have some current I2. All these are AC. Everything is AC. Okay, so this voltage, current, everything time varying. Assume them to be pure now, pure sinusoidal. Okay, everything is AC. Okay, now the definition of an ideal transformer is that it is such a two-port equipment, okay, two-port AC electrical equipment which satisfies the relationship between V1 and V2 like this. V1 by V2 is equal to N1 by N2, and the relationship for between I1 and I2 like this, I1 by I2 and is equal to N2 by N1 for some value of N1 by N2 or N1 and N2. For some value of N1 and N2, you can call it A equal to A, say. Okay, so you can call this ratio as one number A for anything. Okay, A. So if we have a equipment like this, and where these are AC quantities, so this means these are RMS quantities. So everything is AC, and so I1 is the RMS value. Okay, and RMS value. This is also true in terms of peak value, because yes, but okay, in general, you can think this is the RMS value. So if we have such an equipment, we call this an ideal transformer. If any equipment whatsoever has two ports where we have two voltages V1 and V2, two currents I1 and I2, and if this relationship is true, then we call this as an ideal transformer. Is there an ideal transformer in nature or in real life? No, not at all. But what we can get is something very close to an ideal transformer. Okay, so a close approximation to an ideal transformer is just this. So this is the black box, which has two ports. Current here is I1, current here is I2, voltage across this is V1, and voltage across this is V2. Okay, you may ask why I am not putting the plus minus sign. I say that's important. I will put that soon. Right now it's not required because we are not considering the polarity, we are only considering the RMS value. So this relationship is for the RMS value. Okay, so this is not in terms of phasor yet. Okay, I'll put the plus minus sign soon. Okay, so now what you can do to get a close approximation of an ideal transformer, you take a core, magnetic core, and wind two coils on top of it, this with turns N1 and here with number of turns N2, and you connect this. Okay, so now you have to also ensure a few facts, like ensure facts like zero coil resistance. Zero not possible, that means very small coil resistance. You use very thick conductor, maybe made of gold. Okay, zero is not possible, so as small as possible. Secondly, very high, infinite. Okay, theoretically infinite, infinite not possible. So that means very high, infinite permeability of the core. Okay, infinite permeability of the core. So that means the flux will be very high, and also ensured, if possible, non-conducting core. Okay, I mean 2 and 3 is not possible to achieve together. If we want high permeability material, that means we have to use iron or some alloy of iron, and iron is conductor. And if we want, say, non-conducting core, we can use air core transformer, but then the permeability is not infinite, not very high. So 2 and 3 is not, of course, so therefore not possible together. Yes, what one can do in practice, take a laminated core, you may know that, and thereby reduce the conducting effect of the core. So if you make such an arrangement, then it becomes, if you make this arrangement, exactly zero resistance, exactly infinite permeability, and exact zero conductivity of the core, then this will be a perfect ideal transformer. So that is not possible. So take low resistance, high permeability, that will be a close approximation to a ideal transformer. Now, for a practical transformer, of course, we'll have this non-zero, this non-infinite, and if it is iron core, of course, somewhat conducting core. So that is what we call a practical transformer. Now, in a practical transformer, okay, so the previous thing was, so this is for ideal transformer, And for practical transformer, of course, we will have, all the other conditions, opposite conditions, non-zero coil resistance, and then non-infinite permeability of the core, and the core can be conductive. Okay. So for simplicity, we can choose air core. So the conductivity will be, that problem is gone. Okay. So we can choose air core. This is fine. This is sad. This is sad. So non-zero resistance is sad. Non-infinite permeability is sad. So therefore, the relationship between V1 by V2 and N1 by N2, this is not going to be true. It will be not equal. So strictly not equal. Yeah, it can be approximately equal to this, but strictly speaking, it's not going to be equal. Similarly, I1 by I2 is not going to be not strictly equal N2 by N1. So this is so V1 by V2 equal to N1 by N2 is not the rule for a practical transformer. So therefore, you can ask the question, then what are the equations for a practical transformer? Because the ideal equations are not true. So transformer. So what are the equations for a practical transformer? So this is what we will see next. Okay. And for simplicity, we will stick to air core transformer. That means no core loss, no eddy current possible, no hysteresis loss. Okay. So for simplicity, we will stick to a air core transformer. Now, so we have two coils. Air core. So I cannot draw this. This means iron core. So I cannot draw that. So these two coils will of course have some mutual inductance. Call it M. And whenever there is a mutual inductance, I must put some dots to indicate the polarity relationship between the two coils. Otherwise, the diagram is incomplete. Now let me choose the reference direction of this current I1 like this. I2 I can choose like this. I can also choose in the opposite direction, but there is no harm in doing this way. All calculations will change accordingly. Now the EMF across these two terminals, call it E1 T. The EMF across these terminals, call it E2 T. Instead of writing this in terms of instantaneous value, I can also write them as phasor values. I1, I2. So I1, I2, E1, or you can call it V1, V2. No problem, even if you call it E. Okay, so then I call this V1, V2. Okay, because V stands for voltage. I mean, no reason. Okay, fine. So these are phasors. Okay, so I'm not putting these arrows because I have to then put arrows many a times. I'm just bit lazy. Okay, so these are the phasor quantities v1, v2. Okay, without, and these are small letters, instantaneous quantity. These are capital letters, phasor values. Now I choose the reference direction for V like this. So I will always measure V1 as the voltage of this terminal with respect to this terminal. This voltage minus this voltage. Similarly, I will always talk about V2 like this. This voltage with respect to this voltage, or this voltage minus this voltage. Okay, that's my chosen reference. That's what I choose. Okay, now what will be the equations? So let's apply KVL on the primary side, this side. Okay, so in this loop on primary, so what can we write? So from, let's start, so we start from this point and we'll go around like this. We will add all the voltage drops and voltage rises. Okay, so say we start from here, now we go from here to here. There is a voltage rise. I consider rise as positive, so V1, this is the rise. And then from here to here, through the coil, I will have a lot of voltage drops. What are those drops? Drops I will consider as minus. Firstly, there will be a drop due to resistance of the coil. The coil has some resistance. Call it R1, I1. R1 is the resistance of the first coil. Okay, so let me write here. R1 resistance of primary. Similarly, R2 will be resistance of secondary coil. Okay, so KVL, I'll have V1 minus this drop. I'll also have an inductive drop minus j omega L1 I1, because this coil has an inductance, self-inductance, of course. So I write j omega L1 I1. So L1 is self-inductance of primary, and similarly I'll write L2 as self-inductance of secondary. Okay, so this is the voltage. So let's do it once again. V1 rise, then I1 R1 drop, then j omega L1 I1 this phasor drop. Is there anything else? There is one more voltage induced in this coil due to the mutual inductance between these two coils and this current. So this current I2 is flowing in the second coil, which will create an EMF in the first coil. Now what will be the polarity? Will it be, so that, okay, what will be the magnitude first? The magnitude will be, of course, in terms of phasors, j omega m multiplied by I2. Now should it be plus or minus? Let's see. So I2 is leaving, according to the chosen reference, I2 is leaving, going out from the dot, which means here the induced polarity will have minus near this dot, because this current is leaving, going out through the dot, so it will be minus here and plus here. So going down clockwise this way, it is a voltage rise. Okay, So that's a voltage rise. So I put a plus sign therefore, and then here I write this equal to 0. This is the equation for KVL for primary. Similarly, KVL on secondary. So we can do it in the same way. Let's start from here. Okay, let's start from here and go clockwise. Okay, let me go clockwise along the arrow of this, along the direction of I2. Okay, so let's start from here and go like this. So the first thing I will have is voltage drop due to resistive drop. So let me write minus I2 R2. Then there will be self-inductive drop j omega L2 I2. And always, okay, let me take a diversion. Self-inductance is always a drop in the direction of the current. J omega Li is always a drop in the direction of I. This comes from the rule of self-inductance, which we discussed much before. So this rule, from this rule, you can find. So let me write it here. So in terms of phasor, if this is I, phasor, okay, this is the phasor, then j omega Li is always, you can think this as a always a drop along I, same direction. So the voltage V is equal to j omega Li. This will be like this, V plus minus, this is a drop. Okay, this is same as this. Think of it. So this is one small crucial thing which we often deal with always, but we do not possibly say explicitly, but these are the facts. Okay, so self-inductance you can always think like a drop, voltage drop. Okay, so I have resistive drop, then self-inductance drop, then what else? I'll have a mutual inductance, mutually induced EMF. So that will be j omega m multiplied by I1 multiplied by j omega m, then plus or minus. Okay, that's the question, plus or minus. Let's see. This current I1 is entering the dot. It is entering the dot, so that means this side will be plus, this side will be minus. Dot will be plus because current is entering through the dot. Okay, so this will be plus, which means going like this. So I'm going like this. So I have a rise, voltage rise. So I should have a plus. This will be plus. Okay. Now let's come from here to here. I have a voltage drop, plus to minus. So minus V2. This is equal to 0. Okay. So I can write this also by reorganizing. So I multiply everything with a minus sign. So this becomes V2 plus minus minus R. No, this will be plus R2 I2 plus j omega L2 I2 minus j omega m I1 is equal to 0. V2 positive, this is positive, positive, this is negative. Okay, fine. Now, so the question was, what are the rules for a practical transformer? These are the two rules for a practical transformer. Rule number 1 and rule number 2. So these are the equations that a practical transformer obeys. A practical transformer does not obey this rule. This is the rule which a practical transformer obeys. Okay. So the answer is this. Okay. Now, next question. This is the final topic in this video, is to find the equivalent circuit of a practical transformer. What do you mean by an equivalent circuit? An equivalent circuit is a circuit which will again have two ports like a transformer, primary and secondary. Okay, so an equivalent circuit will be some circuit, whatever it is. It will have two ports, of course, and there will be something inside the circuit. I mean, whatever it is, it can be a very complicated circuit, it can be a very easy circuit, it can be a transformer itself, it can be something else, it can be even an electronic circuit, anything. Okay, equivalent means if the voltage here I denote as V1, okay, plus minus chosen reference, current chosen I1 in this direction, current I2 chosen in this direction, voltage V2 with this reference, the reference polarity. See, everything is similar to this practical transformer. So this is a practical transformer. This is the practical transformer. Okay, it doesn't matter. Okay, so this is the practical transformer, and you see that the current I1, I2, V1, V2. Okay, note their directions. I have chosen same direction, similar directions for all of them. Okay, now if the relationship between V1, V2, I1 and I2 in this circuit, in this black box, is same as this relationships, then we will call this black box to be equivalent or an equivalent circuit of the practical transformer. Okay, so if the relation between V1 and V2, similarly I1 and I2, or V1, V2, I1 and I2, everything together, V1, V2, I1 and I2 obeys equation, call this equation 1, call this equation 2, obeys equations 1 and 2, then we call this black box an equivalent circuit to the practical transformer. Why? Because from outside we cannot tell what is there inside. Is it the actual transformer or is it something else? Because from outside the behavior of V1, V2, I1 and I2 will be similar as this thing. So we therefore call this thing as an equivalent circuit, no matter whatever is there inside. It can be a simple circuit, it can be a complicated circuit. Now, an important fact is that equivalent circuit is never unique. What is an equivalent circuit? It is something which behaves in a way similar to the original one from outside, but inside can be a lot of different things. So inside I can have lot of different circuits which will behave in the same way from outside. Okay? So, what is there inside we cannot say. So, therefore, equivalent circuit is never unique. Equivalent circuit is never unique. So, I can design many different circuits which will obey these equations 1 and 2 from outside. So, this is not unique, but we will design or show you one circuit which is most commonly used in electrical engineering. So, we will show you the most practiced, most standard, most common equivalent circuit that people use, but this is not unique. Now, the way I will design this equivalent circuit, once again I am repeating, this is not unique. So, I can design it in many different ways, but I will do it in a way that is common to people. So, what I will do, I will take inside, I will take a ideal transformer. So, I will take an ideal transformer with turns ratio okay. So, the turns ratio will be same as the given turns ratio of the practical transformer. So, equivalent circuit of a practical transformer with turns ratio N1 by N2 is equal to, say, A given. Okay, I will write an equivalent circuit because this is not unique. So, this turns ratio is given. So, what I will do, I will take an ideal transformer N1, N2, okay, and N1 by N2 is equal to A is equal to nominal turns ratio or given turns ratio of the practical transformer. I will choose it this way. I can choose it in other ways as well, that's also possible, but this is my choice. I can make this choice because I know the answer is not unique. So, I can make any choice as long as the relation between V1, V2, I1 and I2 is same as this, and I will show the choice that I am making will obey this relationship. I will show that. Then I will connect this here and I will connect this here, and here I will take 3 impedances connected in the form of T. Okay, so this is a T network, 3 impedances. I will connect this side here, here, and I will connect this to the transformer. So, okay, questions. So, firstly, you may ask, I said ideal transformers do not exist. So, how can I take an ideal transformer? This is only a theoretical circuit. Okay. So, I am not going to make or manufacture this circuit and install it. This is only a theoretical circuit. This theoretical equivalent circuit is useful for doing calculations and for doing simulations in computer. I am not going to manufacture it. This is only a theoretical circuit. Next question, what should be the values of these 3 impedances? That I will calculate and find out, so that the relationship between V1 and V2, I1 and I2 is as desired. Okay, so these are the things I have to find out. Okay, so but before that, I mean, so this is what I'll find out. But before that, I can write this voltage. Let me call this voltage as V2 prime and this current as I2 prime. Now this is an ideal transformer, so therefore I can write, so for an ideal transformer, we know that V2 prime by V2, let me do it here. For the ideal transformer, V2 prime by V2 is equal to V2 prime by V2 is N1 by N1 by N2 is equal to A. This is equal to A. So from this I can write V2 prime is equal to V2A. And similarly I2 prime by I2, I can write this as N2 by N1, this is equal to 1 over A. So from this I write I2 prime is equal to I2 by A. So I write these values here. This is equal to, I write it this side, AV2, and this is I2 by A. Okay. Now I will need these two equations. I have to satisfy these two equations somehow by choosing these impedances, these three impedances. I have to satisfy these equations. So when these equations will be satisfied, we have to satisfy these two equations, and this is the equivalent circuit I have copied here. Okay, we have to find these three values such that these two are satisfied. Now I will just manipulate these two equations a bit. Okay, how so I will put the value of I2 and V2 in terms of I2 prime and V2 prime in these two equations. Okay, so we write in place of I2 I can write this is equal to AI2 prime. Okay, so in place of I2 I write AI2 prime. I have another one here, AI2 prime. Anywhere else? No. Okay. In place of V2, I write V2 prime by A. V2 is V2 prime by A. So here I write V2 prime by A. I do not have any more V2. Okay. Now I do one more manipulation, which is I multiply this second equation with a factor A. So this A and this A cancels. So therefore I will have, let me do it directly. Okay, let me do it directly here. So if I multiply this, then I have, then this A is gone. I will have A here. This will become A square. This A I write inside. Okay, so I have multiplied throughout with this factor A. Oh, okay, this I2 I will also write in terms of I2 prime, because I now essentially want to concentrate only on this part of the circuit, because this is the unknown part. So I want to write everything in terms of the quantities involved here and here. I2 is here, no use. So I will write everything in terms of I2 prime and V2 prime. So this I2 prime also I have to write as, I2 I have to write as AI2 prime. So this becomes another A I2 prime, or okay, let me write this as a square directly. Okay, so and then so from this you see that I have two equations. First one, let me write this as it is, v1 minus, let me take I1 common. Okay, so I1, with this I have R1 plus j omega L1, R1 plus j omega L1, anything else? No, nothing. Okay, plus j omega m a I2 prime. This is equal to 0. Okay, now what I will do, I will add and subtract a term here, which is, so I will subtract a term not prime. So I have then subtracted I1 j omega ma. So I have to therefore add j omega ma I1. Okay, so I have subtracted this term j omega ma I1. Okay, so these two cancels, it's fine. Now actually I can put this inside, that's why I kept this place blank. Okay, so now I put it here, so this will become minus j omega ma I1. So this I can now, it is. You may think I'm doing some complicated things, doing some magics. No, actually. So I know what I want to do finally. I want to finally write two KVL equations in terms of these two voltage and these two currents. Okay, so what I want to do, I want to write two KVL equations here, one KVL in terms of this voltage and this current in this loop, in this mesh, another KVL here in this loop. So I just want to write two KVL equations. Okay, so the KVL equation in this will be of the form V1 multiplied by some drop I1 times this impedance, and then here this impedance multiplied by I1 minus I2. So I want to write it in that way. So that's why I am doing this manipulation. Okay, so I'm not doing any magic. I know what I want to do. I want to write two KVLs, and keeping that in mind, I'm manipulating these equations. Okay, so therefore you see I have this V1, and then this impedance I can write here. Okay, call this is equal to R1 plus j omega L1 minus j omega ma. This is this value. Okay, so then I have this drop, this times I1. Okay, and then let me call it j omega ma. This is I call as j omega ma, this impedance. Okay, then I will have j omega ma multiply, so this current is how much? I1 minus I2 prime. This is this current, I1 going like this clockwise, I2 prime in the opposite direction. This is I1, this is I2 prime. Okay, so this is the KVL equation for this loop, and with this I actually have found this value. Similarly, let's manipulate the second equation, and let me write this as V2 prime plus, let me take I2 prime common, and then I will have a square R2, this one, plus a square omega L2, a square omega L2 j. Okay, and then let's keep some space if I need it. Then I have minus j omega A M I1. Okay, this is this term. Now I will do this. I will subtract I2 prime, which means I am adding the quantity I2 prime times this, so I have to subtract it, j omega am I2 prime. Now I put this inside the bracket, so it becomes j omega am, and I erase it outside. So these two are same as this two, but I just wanted to write it in the form of two KVLs, two mesh equations. So you see here I have say, let's starting from here. I needed this symbol, plus and minus. Okay, this is plus and minus because this is plus and minus because these are the dots also. Okay, so you see now the KVL equation says V2 drop here, then the drop. Okay, then the drop here. This is j omega ma times, this is actually a rise because I1 minus I2 is flowing in this way. Okay, I1 so this is a rise. So I have a minus. This is drop, this is rise. And then here I have another drop, which now if I take this impedance equal to this value, okay, I do not have space to write, so this impedance is equal to this value. You see this KVL is satisfied. So what I have done, you just verify it yourself once that the KVL equation for these two KVL equations with the value of this impedance equal to this, the value of this impedance equal to this, and the value of this impedance equal to this is same as these two equations. So these two KVL equations are same as these two equations, which mean if I choose this impedance, to be this equal to this, and this equal to this, then the overall equation between V1 I1 and V2 prime I2 prime will be like this, and that means the overall equation between V1 I1 V2 I2 will be like this. Let me state this once again, summarize this once again. Verify yourself. If I choose this impedance to be this impedance to be this impedance to be this, and if I have this transformer, an ideal one with N1 N2 equal to A, given value of A, then the relationship between V1 I1 V2 I2 will be same as this one, same as the practical transformer. So this is therefore is going to be a equivalent circuit of the practical transformer, equivalent circuit of the given practical transformer. Okay, so this is the equivalent circuit, and in which now we can redraw this impedance like a series combination of a resistance and an inductor. So this resistance is R1 and this inductance will be L1 minus MA Here you can write this only as an inductor, whose value will be of course MA, where M is the mutual inductance between the two coils. Then this one you can also write as a resistance whose value is R2 square. So this is R2 A square. A is the turns ratio of the nominal turns ratio of the practical transformer, and this you call as L2 minus M by A. Okay, so this is the equivalent circuit, and we give them names, like we call R1 is the resistance, primary side resistance as referred to, so you can call it primary side resistance. R2 multiplied by A square is the you can call the secondary side resistance as referred to primary. This is called so, and because of this factor A square, you call it as referred to primary. And then this factor you call L1 minus MA is called the leakage reactance, primary side. This factor L2 minus M by A, I think there will be a overall A square factor I have missed. Yeah, there is a square. This, I think there should be a square, right? Yes, yeah. So this will be leakage reactance of secondary as referred to primary. Okay, so this is called the equivalent circuit, and so that's what we needed. I mean, before we can proceed. So basically, in this class, this is an additional video. It's not part of the main course measurement. This was an additional video. It was a complete, in a sense, I don't know how complete it is, a recap of all the background knowledge one needs about magnetic circuit, transformer equivalent circuit, which will be helpful in understanding CTPT instrument transformer in more detail. Okay. Okay, so let's take few more minutes to just show you a nice interesting fact. Okay, so if you like, so you can simply erase it. This will also become 0, because that's the condition for an ideal transformer we have written. Okay, see here, going back. So for an ideal transformer, the coil resistance should be 0. So R1, R2 will be 0. Okay, and then I'll show you that this will also be 0. This will also be equal to 0. Why? So the practical transformer. So this is equivalent to this practical transformer, right? Dot M. So this is the mutual inductance. This side I have R1, L1 self inductance, R2 resistance, L2 self inductance. So this is actually the equivalent circuit of this. Now, if I have, say, very high permeability, the core material, then all the flux that is created will link through the secondary coil. If current I1 is flowing it will create a flux phi t, it will go completely through the other coil. Okay? Phi 1 t will link second coil completely. So then we can write that, so if so, so how much is then L1? L1 is nothing but this is the EMF. So we can write EMF induced, or across the first one we can write E1. So assume this is open, so this side is open and this side is excited. Okay, so E1 self-induced EMF, not the resistive drop, ignore the drop, and R1 is 0, actually R1 is equal to 0, so R2 is equal to 0. Okay, so E1 is therefore this voltage is E1, this is L1 multiply, or let me write this as first, N1 times phi, this is flux linkage, ddt. Okay, and this is E1, and how much will be E2? E2 will be ddt of into phi, call it phi 1 because this is due to current 1. Okay, so E1 now, if, and we also write that, we also know that E1 is equal to j omega L1 I1. Similarly, we also write that E2 is equal to j omega M I2. But this two equation says that from this two we can write that E1 by E2 is equal to N1 by N2. But from these two equations we can write E1 by E2 is equal to how much? L1 by M. Now if this is true, this is also true, so then from this and this, okay, then we can write M by L1 is equal to N2 by N1, or 1 over A. So M is equal to L1 by A. Okay, and if so, now if you put the value L1 by A, you see this is becoming 0. Similarly, a homework, you can show that this is also equal to 0. Homework. With a similar analysis, you can show this is equal to 0. Okay, so that's okay, so that's what happens for an ideal transformer. All these things become 0. Okay, so that's it. So we had a long class, but this is actually a recapitulation, review of all the elementary concepts required to understand transformers better, and also this M will be very high. So this will be infinite for an ideal transformer. Why? Because we have said that that permeability of an ideal transformer should be very high. Permeability is tending to infinite, so this will imply M tending to infinite. Why? Because more permeability means more flux, okay, more flux with less current. Now more flux means there will be more EMF. Okay. So, that means with less current we will have more EMF. So, of course, the impedance will be high. Impedance is proportional to M. So, M will be high. So, if permeability tending to infinite, you can show M is equal to infinite, tending to infinite. Okay. So, this also, let this be also a homework. You think that if permeability is high, then this is infinite, and if so, then you see this is 0, this is 0. So, you can virtually short circuit this. So, you can do it like this. So, you can short circuit this. This is not there. You can also short circuit this. This is not there because these are 0, and similarly this is infinite, means you can keep it open, right. So, if we assume that the resistance is 0, the permeability is infinite, then it boils down that this is 0, this is 0, this is 0, this is 0, this is infinite. So, this branch you can forget, this branch you can forget. So, this point is directly connected to this point is directly connected to this, and none of this is present. So, inside this box we have only this ideal transformer. So, this was the ideal one. So, what we have shown is that with the assumption of very high permeability and low coil resistance, this equivalent circuit of a practical transformer boils down, becomes same as an ideal transformer only. That is interesting. Okay. So, thank you.